Hello everybody, welcome to this video starting to look at section 7.8, which is improper integrals. So improper integrals are split into two types, type 1 and type 2, which makes it rather easy to divide into two videos. So in this video, we're going to start with improper integrals of type 1. So the point of this section is going to be to expand our knowledge, our consideration of integrals in two directions. So let's get started. So back when we defined integrals, we defined them over closed bounded intervals a, b. So our intervals where we were integrating were from a to b of f of x dx. We were supposed to have finite length, and the functions were supposed to be defined at the endpoints. And then when we did that, the tactic was that we split up AB into a bunch of little pieces. We added up areas of rectangles on each little piece, and then we took the number of rectangles to infinity. And we said that this makes sense whenever f is continuous or if it has at most a finite number of jump discontinuities. So all the integrals that we've considered until now were over closed bounded intervals, and the function was continuous, or at most it had a couple of jump discontinuities. So definitely no infinite discontinuities or anything like that. So now we're going to expand this in two directions. So first we're going to study in this video what happens if our interval is infinite. For example, how could we integrate over an interval that looks like 0 to infinity or minus infinity to infinity, or any kind of interval with an infinite endpoint? How can we integrate functions over those? And then secondly, in the next video, we're going to study integrals of type 2, improper integrals of type 2, which is what if the function has an infinite discontinuity at one of the endpoints or in the middle? For instance, could we integrate 1 over the square root x or 1 over x squared on 0, 1? Noticing that at 0, these functions are going to go off to infinity. So how would we integrate these types of functions if we can at all? And the strategy is going to be not to go through the whole definition of the integral again, and make some adjustments. I know people seem to find the definition of integral really challenging. But the strategy is going to be to use what we know, which is how to integrate functions over how to integrate continuous functions over closed bounded intervals. So use what we know to calculate some things and then take limits. So let's see how that works. And it's going to be pretty mechanical. So it's going to be a pretty mechanical section. As long as we understand what's going on, we can do it. Okay, so let's suppose we want to integrate a function from a up to infinity. So it could be from 0 to infinity, 1 to infinity, anything, some constant up to infinity. How could we do that? Okay, well, one thing that we could do is rather than integrating all the way from a to infinity, which we don't know how to do, we replace infinity by some number. Say instead of going to infinity, we could integrate up to 10, or we could integrate up to 100 and so on. So we integrate up to some number t. We look at what we get. It's going to be a quantity depending on t, right? If we're integrating up to t, the signed area up to t, it's going to depend on t. We look at that quantity. It's a quantity depending on t, and then we take the limit. Okay, and that's going to be what we mean by the integral from a to infinity. Okay, so just to say that again, rather than integrating all the way from a to infinity, which we don't know how to do, we replace infinity by some number, say t, that's going to be a variable. We integrate up to t, we get an answer in terms of t, and then we take the limit as t goes to infinity, see what we get, and if the limit exists, we say that the improper integral exists. Okay, so for instance, rather than integrating from 0 to infinity, you would integrate from 0 to 10, 0 to 100, 0 to 1,000, 0 to 10,000, and see if there's a pattern. If there is a pattern or a limit, then that would be your infinite integral. Okay, similarly on the other end with integrals going to minus infinity, right? Rather than integrating from minus infinity up to some number b, which we don't know how to do, right? We don't know how to integrate from minus infinity to 0 just yet. We replace that minus infinity by some other variable, some number t. We integrate from t to b. That's going to give us an answer in terms of t. And then we look at the limit of what happens as t goes to minus infinity. And if that limit exists as a finite number, then we say our improper integral exists. Okay, so just to make it a little bit concrete, if we wanted to integrate a function from minus infinity to 0, we could try to integrate from minus 10 to 0, minus 100 to 0, minus 1,000 to 0, minus 10,000 to 0. And we could see if it settles down to a finite number, in which case that would be our improper integral. Okay, and then a couple of easy extra comments is if we say, if these integrals exist, if the limits on the last slide exist and they are finite numbers, when you say that we said the improper integral is convergent. If not, we say it's divergent. And how do we define two-sided improper integrals? So if we want to integrate all the way from minus infinity to infinity, well, we just cut it off somewhere in the middle. Say we cut it off at 0. It doesn't really matter where you do the cutting. And we look at whether we can integrate first from minus infinity up to a, and then from a up to infinity. And if we can do both of those, then we say that the improper integral from minus infinity to infinity exists, and it's the sum of the two. Okay. So rather than making both sides infinite or minus infinite, we just consider them separately and then we add them together. Okay, so let's see some examples. Or first I should comment, what is the kind of geometric meaning of this? For instance, if we focus on the integral from a to infinity, we said that the integral from a to b of a function is the signed area under the graph of f of x and above the x-axis from x equals a to x equals b. And here it's just the same story going all the way up to infinity. So normally it's bounded by x equals a and x equals b. Here it's not bounded by x equals b. It's just the signed area under the graph to the right of x equals a. And sometimes that might be finite, but sometimes it might be infinite. Okay, so let's see some examples. So first, let's look at, does the integral from 1 to infinity of 1 over x converge? Pretty classic example. So remember what we said, if we want to study the improper integral, the strategy is to replace infinity by a t, calculate the answer in terms of t, and then look at what happens as t goes to infinity. So let's first calculate the integral from 1 to t, where t is just a kind of placeholder. So we look at the integral from 1 to t of 1 over x. Now it's a definite integral, so we can use all the tactics that we're used to. We find the antiderivative of 1 over x is ln absolute value x. It's a definite integral. We have to plug in 1 and t. We plug in t, we get ln of t. Since t is supposed to be positive here, we can remove the absolute value. If we plug in 1, we get ln of 1, and ln of 1 is, of course, 0. So this integral is ln of t. And then we notice that this depends on t, and we can just take the limit of that. So then we're supposed to take the limit of the integral from 1 to t. We found that the integral from 1 to t is ln t, so we can take the limit of ln t. And then if we remember the graph of ln t goes to infinity as t goes to infinity. Okay, so the integral from 1 to t of 1 over x tends to infinity as t goes to infinity. That exactly means that the improper integral diverges. So this is a divergent improper integral. So just to recap, all we did is we replaced the bad point by t, work out the answer in terms of t, then let t go to infinity. And since the result was infinity, we said the improper integral diverges. Okay, so let's look at another example. The only thing that's different here is we're replacing 1 over x by 1 over x squared. And we're going to copy all the same steps and see what happens. So we're trying to find the improper integral from 1 to infinity. Let's replace infinity by t, work out the answer in terms of t, and then take the limit. So we look at the integral from 1 to t of 1 over x squared. We take the antiderivative, that's minus 1 over x. We plug in t, we plug in 1. We get minus 1 over t plus 1, so 1 minus 1 over t. And now to find the improper integral, we're supposed to take the limit of that as t goes to infinity. So we take the limit of the integral from 1 to t. The integral from 1 to t, we just worked out, it's 1 minus 1 over t. So we're taking the limit as t goes to infinity of 1 minus 1 over t. Okay, and the 1 over t piece goes to 0, so we're just left with 1. So in this case, we followed all the same steps, but because the antiderivative and the function was different, we got a very different answer, right? Here, the limit exists and it's a finite number. So that means that the integral from 1 to infinity of 1 over x squared is convergent. So this is a convergent improper integral with value 1. So it depends quite finely depending on what the function we have is that we're trying to integrate. Okay, so let's just compare these. So we said in the first example that the integral from 1 to infinity of 1 over x is divergent, but the integral from 1 to infinity of 1 over x squared is convergent. So what's kind of the meaning here? Since we said the integral from 1 to infinity is supposed to represent somehow the area. So why would it be the case that intuitively 1 over x has infinite area, but 1 over x squared has finite area? Well, if we think back of what 1 over x squared and 1 over x looks like, if x gets to be a big number, if we're looking far to the right on the graph, x squared is larger than x, which means that 1 over x squared is smaller than 1 over x, right? For instance, if x was 10, 1 over x squared would be 1 over 100, 1 over x would be 1 over 10. So 1 over x squared goes to 0 much more quickly than 1 over x, and that's what allows it to have finite area, even though we're integrating all the way up to infinity. So it depends quite carefully on the function how fast it's going to 0 as x goes to infinity or minus infinity. But let me emphasize that this is important for intuition and for understanding what's going on, which I think is really important in math. Otherwise, you just get lost. But it does not replace the calculation. So please don't write something this vague in an exam. But I think it's important for understanding and knowing where you're going and knowing why you're doing it. Okay, and of course, there's nothing special with the powers we talked about here, the 1 over x, 1 over x squared. You could look at every power, say 1 over x to the p, and do the same calculation. And if you do this, you get something called the p-test. So if we look at the improper integral from 1 to infinity of 1 over x to the p, then depending on p, this might be convergent or divergent. If p is strictly bigger than 1, it's convergent. If p is less than or equal to 1, it's divergent. In particular, when p equals 1, then we have 1 over x. Okay, we saw that's divergent. But when p equals 2, we saw that with 1 over x squared, then it's convergent. So that agrees with what we saw in those examples. But this characterizes all the different powers. Okay, for instance, you might have to apply this in settings where the p is kind of hidden. So for instance, if we wanted to look at 1 over x squared x, that's 1 over x times x to the 1/2. So we could rewrite this as 1 over x to the 3 over 2. Then we would have p is 3 over 2. 3 over 2 is bigger than 1. Okay, this will be convergent, for instance. Or if we wanted to look at the integral from 1 to infinity of x dx, okay, it's tempting to think here it would be x to the 1, so p equals 1, but remember this is for 1 over x to the p. So if we wanted to write x on the bottom, we would have to flip the power. Instead of having x to the 1, it will be 1 over x to the minus 1. So we could write this as 1 over x to the minus 1, then p would be minus 1. Okay, we would be in the divergent camp. Okay, so sometimes you might have to apply these in hidden places. You have to figure out the value of p, and then based on what the p-test tells you, you can decide if it's convergent or divergent. Okay, but these are only for things that look like 1 over x to the p. Of course, there are many more improper integrals that we might have to consider than that. Okay, so let's look at some. For instance, with negative infinity, does the integral from negative infinity to 0 of 2 to the r dr converge or diverge? If it converges, let's find the value. So this one is improper where we're going on the left, we're going all the way to minus infinity rather than going to plus infinity. But the strategy is going to be the same, right? We replace the bad endpoint, the minus infinity, by a t, work out the answer in terms of t, and then we let t go to negative infinity. Okay, so if we look at integral from t to 0, now it's a continuous function on a definite integral. We can use fundamental theorem of calculus. We find the antiderivative of 2 to the r, that's 2 to the r over ln2. We plug in the endpoints, remembering that anything to the power of 0 is 1. So we get 1 over ln2 minus 2 to the t over ln2. And then we have to take the limit of that as t goes to negative infinity. So that means we take the limit as t goes to negative infinity of 1 over ln2, which is a constant that stays the same. And then 2 to the t over ln2, if we think about the 2 to the t, which is the only piece that depends on t, what happens to 2 to the t as t goes to negative infinity? That means we're plugging in large negative numbers. So for instance, if we were to plug in t equals minus 100, we would have 2 to the minus 100, which is 1 over 2 to the 100. 2 to the 100 will be a huge number. So we have 1 over a huge number that's going to go to 0. So actually the second piece goes to 0, and we're just left with 1 over ln2. Okay, so this converges to a finite number. That means the improper integral exists, and it converges to 1 over ln2. Okay, so everything is pretty much the same. It doesn't matter if you're going to infinity or to negative infinity. Just replace that bad endpoint by t, work out the answer in terms of t, and then let t go to either infinity or to negative infinity. Okay, lastly, let's look at one which is infinite on both sides, so minus infinity to infinity of 1 over 1 plus x squared. And the strategy is to split this into two one-sided improper integrals. So let's split at 0. It doesn't matter where you split, but sometimes if you pick a good point, then it's going to make your calculation a little bit easier. So here, let's do 0. So first we look at the integral from 0 to infinity of 1 over 1 plus x squared and the integral from negative infinity to 0 separately. And we need both of them to exist in order for the two-sided improper integral to exist. So if we start with 0 to infinity, that means we have to replace infinity by t, work out the answer in terms of t, and then take the limit. So if we look at the integral from 0 to t of 1 over 1 plus x squared, that is a standard one, which is arctan x. We plug in t, we plug in 0. We get arctan of t, and then arctan of 0 is, of course, 0. So we're left with arctan of t. And then we have to let t go to infinity in this. So that means we have to let t go to infinity in arctan t. Okay, what happens to arctan of t as t becomes very large? So you could either think back to the graph of arctangent, or if we use the fact that arctangent is the inverse of tangent, we're asking, what is the value of arctan t if t is very large? It's the same thing as saying, what do I have to plug into tangent in order to get something very large? So, and what do we have to plug into tangent to get something very large? We have to plug in pi over 2, for instance, or a number close to pi over 2. So you can kind of reason it that way using the relationship between tangent and inverse tangent. Okay, so the improper integral from 0 to infinity exists. It's convergent to pi over 2. And then you could do the same thing on the other side, right? So you could do t to 0, and then you could let t go to negative infinity, and you'll get the same answer, pi over 2. It's just the same calculation, but with something swapped around. So both of the one-sided improper integrals converge. Hence, the two-sided improper integral converges to the sum. In this case, that's pi over 2 plus pi over 2, which is pi. Okay, so just to summarize what we talked about in this video, we focused on improper integrals of type 1, which is where the length of the interval that we're integrating over is infinite. And there are several types. They could be infinite at the right side, infinite at the left side, or infinite at both. For instance, if it's infinite at the right side, we replace the infinity by t, work out the answer in terms of t, and then take the limit as t goes to infinity. And then with easy modifications on the left, And then for the two-sided ones, we split it up into two one-sided ones. Okay, that's it for today. Thanks, everyone. See you next time.